In this video, we'll have more examples of circuit analysis that use Thevenin's theorem. In this example, we're tasked to determine the Thevenin's equivalent circuit as seen by the 20 ohm resistor. So in this problem, this really means that we want to know the Thevenin's equivalent of the circuit surrounding the 20 ohm resistance, which is really this circuit. Once we uh, determine that that would turn the circuit with respect to the 20 ohm resistance into something like this. So let's proceed in finding VTH and RTH. So we need to focus on this circuit that we need to convert into Thevenin's equivalent with the 20 ohm resistance removed. And then compute for the voltage VOC across the open terminals with its proper polarity. Now, in order to compute for the voltage VOC, we need to find a simple or the simplest loop that traverses VOC and does not contain any current source. And that loop would be this one. Okay, so it traverses VOC and there is no current source whatsoever. Okay, now to write KVL here in this loop, we need to know the current passing through the 10 ohm resistance and the 5 ohm resistance. Now, when we remove the 20 ohm resistor, uh, it should be observed that this current source here will flow uh, directly. This current here will flow directly to the two resistances. Okay, so that means that the current through the 10 ohms and 5 ohms is 4. For the 10 ohms, the current here is so the current here for the 10 ohms is in that direction, and that is 4 amperes. Okay, and the current through the 5 ohms is in this direction, which is also 4 amperes. Okay, so this 4 amperes here flows directly through the two resistances. It's because this part here is already open and the current has nothing else to go but through those resistances. Now, based on the direction of the currents through the resistances, the polarity must be, it is positive here for the 10 ohms and it is negative here, and for the 5 ohms it is like this. Okay, so now that we have the currents and the polarities of the voltages across those resistances, we can now write the equation for the loop that we have chosen, and that involves the voltage VOC. So this is the equation. Okay, so this is the equation, and from this equation, we can immediately determine the voltage VOC, which becomes our voltage VTH. Now for RTH, again, we need to concentrate on the circuit, but this time without the uh, independent current sources or the independent current source. So we need to remove this one from the circuit, and that would give us a circuit that would look like this. Okay, and we then so these are the open terminals again. So we then compute for the resistance looking at the open terminals. Take note that the circuit contains no contains no dependent sources, so therefore we can use case 1 in finding RTH. And that is simply equals to the sum of the two resistances, which is 15 ohms. Okay, so that is the resistance, and therefore we can now draw our modified circuit with respect to the 20 ohms, which is like this. So this is our VTH, this is our RTH, and this is the final answer. So based on this circuit, we could get the current that flows through this resistance, or we can find the voltage. In this example, we are required to determine the current I sub naught, which is the current through the 4 ohm resistance. Take note that this current is the same current that flows through the 12 volts, since these element and these elements are in series. Take note that we are required to solve this problem using the Thevenin's theorem. We could have solved this problem in other ways, like using mesh analysis. So if we use a mesh analysis, for example, that would result into 4 loops of loop currents, or if we solve this using nodal analysis, that would give us uh, this node, and this node. So that will result into the 3 nodal voltages that is required to be solved. But the problem states that we will solve this using Thevenin's theorem. Okay, so the first step is identify the part of the circuit that you want to convert into a Thevenin's equivalent. So it should be complicated enough to warrant a conversion. So we could look at several parts here. So maybe you want to convert this part, or maybe uh, just this part, but it looks very simple, or maybe this part. Okay, so let's use this part uh, as our candidate for conversion. So if we convert this part, that means that we're trying to replace this part with a voltage in series with a resistance, and that the circuit would become like this. Okay, so this part here is really this part again, and this part here, the remaining part would be this part here. Okay, to solve for VTH, we detach the circuit that we need to convert to Thevenin's. So this is the circuit here, and from the circuit we um, determine the voltage across the open terminals. So these are the open terminals here and here, along with the correct polarity for that voltage. Uh, to solve for VOC, we look for a loop that contains no current source. So this seems to be the loop that we need. A loop also that traverses VOC. To write the KVL equation, that would require us to determine, to know the current through the 3 ohms, 2 ohms, and 5 ohms to get this current. So the direction of currents there are arbitrary. You could use a different direction to determine the currents through these resistances. we can use mesh analysis to solve them. So let's say I use mesh analysis, so therefore I uh, I indicate my loop currents through the loops. So let's say this is my first loop here. So let's say this is my loop current here. So I'm using here a counterclockwise direction for the loop. Here I also use a counterclockwise direction. Here there is no loop current because this is an open circuit, so therefore the loop current there is 0. Now, why did I use a counterclockwise direction for the loop currents? It's because I want it to be the same to the direction of the existing currents here. So we have 4 amperes and 2 amperes. Now, because they are in the same direction as the loop currents, so therefore this loop currents becomes 4 amperes. Here this becomes 4 amperes, and this one becomes 2 amperes. Okay. To get the current through the resistances, the actual currents, we we determine the loop current that passes through the resistances. For example, the current that passed through the 3 ohms is the loop current. Here, this is the 4 ohms or the 4 amperes. So there is no loop current here, so therefore the actual current that is through the 3 ohms would be the same as the current, the same as the loop current, which is 4 amperes. For the 5 ohms, we also determine the loop current that passes through the resistance, and we notice that the loop current that passes through there is also the loop current 2 amperes. There again, there's no other loop currents on this side because the loop current there is 0. So therefore, the current through the 5 ohms is also the loop current 2 amperes. Now for the 2 ohms, the loop current that is supposed to pass through that resistance is this loop current, but this loop current is 0, so therefore the current here is a 0. Okay. Then we also indicate the polarity of the voltage across the resistances. So here this is positive, this is negative based on the direction of the current. So this is positive, this is negative, this is positive, this is negative, but the voltage here is actually 0 because the current there is 0. We can then proceed to write our KVL equation starting from here. We go around clockwise. So starting in at this point, so the KVL equation would look like this. Okay, so minus VOC plus 3 times the actual current 4 amperes plus 2 times the actual current, which is 0, and then on to the 5 ohms, that would be plus 5 times the current 2 amperes equals to 0. So from here we can solve for our voltage VOC, which is 22 volts, which also becomes our voltage VTH. Now for the resistance RTH, we can use the same circuit provided we disable all the uh, independent sources. So we disable this one. So that means we need to open the terminals. So that is effectively detaching or removing that source. And likewise for this, we remove this source. So we have a circuit that looks like this. Okay. And from the circuit, it's a simple series circuit. So therefore, you will get there RTH to be equals to 100 ohms. Our modified circuit now becomes this one. So this circuit is much simpler compared to the original circuit. So how are we going to solve for I sub naught? Again, we can use several tools. We can use mesh again or nodal. Now let's say we use nodal analysis here. So we can specify this part to be our ground node, and we label the remaining nodes. So let's say this is V sub 1 here. Well, this node here is already 22 volts, okay, owing to this um, source, and this node is also 12 volts. Okay. We also need to specify branch currents. So let's say we have your branch current. Um, let's call this I sub 1. And let's say we have a branch current here. So the direction here is arbitrary. Here we don't need to specify a current because we can use the current I sub naught. Okay. So let's formalize those variables and directions. Okay, so those are the branch currents and the nodal or the node voltages. And we note that this is again 22 volts here, and here this is 12 volts. Okay, so then we write a KCL equation. So the Kirchhoff's in nodal analysis we use Kirchhoff's current law. So we utilize this node to write our KCL. So current entering minus current leaving equals 0. So current entering that node, so I sub naught and I sub 2 minus current leaving that node, which is I sub 1. We replace these currents by the node voltages. So for example, I sub naught is equals to 12 minus V sub 1 divided by 4. I sub 2 is 22 minus V sub 1 divided by 10. And I sub 1 is V sub 1 minus 0. So the voltage or the node voltage on the node that we specify to be our ground node is always 0 volts. So that's V sub 1 minus 0 or simply V sub 1 divided by the resistance 10 ohms. So we use these expressions to replace current, the currents uh, the currents in our KCL equation. So this is the new equation. So this is a one variable in one equation. So we could solve for the node voltage V sub 1. Okay, we could multiply this equation by 40, the lowest common denominator, or 20, I mean. So, but I will use 40 here. So multiply both sides by 40. That would mean that the equation will now look like this. And solving for V sub 1, I will get here 11.56 volts. So this is my node voltage, V sub 1. Then I use this equation to solve for I naught. So doing that, that will give me 1/9 amperes for I sub naught. For our last example for Thevenin's theorem, here we are simply asked for the Thevenin's equivalent of this circuit with respect to the terminals A and B. So here we have a dependent current source whose magnitude is dependent on the voltage across the 60 ohms with the polarity indicated. So we need to determine VTH here and RTH. So for VTH, we need to know the open circuit voltage between the terminals A and B with the polarity indicated. Now take note that VOC here is also the voltage V sub X because A and B is parallel with 60 ohms. So therefore, that makes VOC equals to V sub X. Now to solve for V sub X, we need to know the current here. Okay, so let's specify currents so that we can get V sub X. So let's say I have here current, also have here current. So these are arbitrary currents. So let me specify that formally. So in the 12 ohms, we have I sub 1, and through the 16 ohms, we have I sub X. To solve VOC, uh, so I said that this is equals to V sub X. Now we can write a KVL equation through this loop. Okay. Now take note that we'll solve this using the traditional way of solving the problem, not using mesh analysis or nodal analysis in solving for VTH. So that means that we look for loops here that has no current source in order to write a KVL equation, and we also look for nodes from where we can write a KCL equation. So first, I use this loop here to write a KVL equation, and that equation is this one. So starting here, minus 30. Uh, so here, this is our polarity in the 12 ohms. So plus 12 I sub 1, and then plus 60 I sub X. So that is our first equation. So rearranging that equation, that becomes our first equation. Then we can use KCL here. So take note, this is a node. And we can use KCL there to produce another equation. So currents entering that node minus currents leaving equals 0. So current entering is I sub 1, current leaving is I sub x, and 2Vx. Take note that 2Vx is the current, a dependent current source at that. So that becomes our second equation. Now, we now have three variables, and we need one more equation in order to solve the three variables, I sub 1, I sub x, and V sub x. And that should come from this resistance here, because we can relate V sub x and I sub x using Ohm's law. So the Ohm's law there is simply V sub x is equals to 60 I sub x. And rearranging, we get this equation. So we simply transfer this one on the other side. So that becomes this equation. So we now have three equations, three unknowns. And we should be able to solve the variables. And that would give us these values. So again, as I've said before, V sub x is equals to VOC, which is also our voltage V sub TH. Now let's solve for our RTH. So we use the same circuit, but we remove the independent source. So we remove the 30 volts there, but we leave the dependent source behind. So here is our dependent source. Now, because of the presence of the dependent source, we cannot use case 1 to solve for RTH because we cannot combine 60 ohms with 2Vx. So what we need to do is apply an external source, a test source. So let's say we apply a voltage source equals to 1 volt, attach that to our circuit, and then determine this resulting current. Let me specify the current through the 10 ohms as I sub x. Now I will use KCL on this node. So current entering minus current leaving equals 0. So that will give me this equation here. So I sub test, which is the entering current. So this is I sub test here minus the current leaving I sub x and the current dependent current source to Vx. So this is my KCL equation. So that means I can solve for I sub test using this equation. All I need to know is what is I sub x, what is V sub x. Now take note the 10 ohms is directly connected to the voltage 1 volt. So that means that my V sub x must be equals to 1 volt, which by Ohm's law is also equals to 10 I sub x. So I can solve for my I sub x, and that is equals to this value. Now that I have determined the I sub x and V sub x, I can now get my test current, which is 2.1 amperes. And that let and that uh, lets me solve my RTH, which is equals to the voltage 1 volt divided by the test current that I've earlier solved, and that should give me this resistance. So that's it for this video and for Thevenin's theorem. And on our next videos, we will discuss Norton's theorem.